Hello, everyone. My name is Megha, and I'm a second-year PhD student at Monash University. And today I will be talking about Timmy, who dared to drink from the Holy Grail. So most galaxies have supermassive black holes at their centers, which are surrounded by stars. One such star is our friend Timmy, who got close to the black hole and encountered a tidal disruption event. So in a tidal disruption event, the gravitational forces of the black hole can overcome the self-interaction forces of the star, and the distance at which this takes place is called the tidal radius, given by the formula above. You can have two different outcomes. So one is a partial tidal disruption event where the star survives and leaves behind a remnant, and the other one is a full tidal disruption event, as shown in this figure, where the star is completely ripped apart and no remnant is formed. So the strength of these encounters is parameterized using a ratio of the tidal radius with the pericenter distance, called as the beta parameter, as shown here. In these slides, whenever I show you any figures, there would be beta parameters mentioned, and I want you to think that a big beta value means a stronger encounter with the black hole and hence more mass loss compared to a lower value of beta. So it's been argued that about 100,000 stars in the galactic center of the Milky Way have had an encounter with the supermassive black hole at some point. So to understand the post-disruption evolution of these remnants, we used two different codes. So we used a stellar evolution code called Kepler, and we used the three-dimensional smooth particle hydrodynamics code, which was mentioned in the previous slides as well, Phantom, for our simulations. The paper actually has been published in MNRAS now, so these slides are outdated. So we firstly generated models in Kepler, and then we disrupted these models in Phantom. And after that, we mapped these models back into the stellar evolution code to understand the post-disruption evolution of these stars. So what did we find? So we found that, as shown in this figure, the stronger encounters result in more mass loss. So this figure here shows, so this one actually shows the HR diagrams of the three models that we used. These are not the results. This is just showing the models that we used for our simulations. So we used zero age main sequence, middle age main sequence, and terminal age main sequence for 1, 3, and 10 solar mass stars. So in total, we had 9 models. Then we mapped these models into Phantom, and then we disrupted them with 1 million solar mass black hole. All the stars were modeled as 1 million SPH particles. We considered general relativistic effects. The black hole had no spin, and we used a Schwarzschild metric. So as you can see in this one, a star gets close to the black hole and it loses some mass. In this case, it's only about 10% of its initial mass. And as you can see here, the beta value is only 0.85, which is very small. And that's why it's like a weak encounter. But if we have a 1.549 beta value, the star loses about 80% of its mass, as shown here. So it's initially completely stripped apart, but then the material starts falling back onto itself and forms a remnant. Yeah, so eventually something which looks a bit spherical forms, but these remnants have streams of material around them as well. So now let's talk about the results. So we found that the stronger encounters result in more mass loss, as shown in this figure, which shows the remnant of mass of the remnants on the y-axis and the strength of the encounters on the x-axis. So if we look at just the orange lines and look at the 1 solar mass 0 age main sequence model and the terminal age main sequence models shown in dotted lines and dotted dashed lines, we can see that more evolved stars can survive the encounters for bigger beta values compared to less evolved stars. And it's because as the stars evolve, they become more dense in the core, the radius is also larger, which makes them resistant to the gravitational forces of the black hole for higher pericenter distances. We also found that these remnants can spin faster after the encounter. So this figure here shows one remnant formed by disrupting a 3 solar mass middle-aged main sequence star. It left behind a remnant with a mass of 2.06 solar masses. As we can see here, there is formation of vortices, which results in angular momentum transport from the outer layers to the inside of the star, making the central regions rotating faster than the outer layers, which is contrary to what we expected. We expected that the tidal forces would make the outer layers rotate faster than the inner regions of the star. So we also found that these remnants can undergo composition mixing. So this figure here shows the nitrogen-14 composition for 3 different models. So 1 solar mass, 3 solar mass, and 10 solar mass middle-aged main sequence models for a range of beta values. Again, higher beta values mean stronger encounters, which means more material is stripped away from within the star, which results in more nitrogen mixing as well in these remnants. So the main goal of our work was to map these models back into the stellar evolution code and to understand the post-disruption evolution of the remnants. This is an HR diagram of 1 solar mass star, which was generated in our stellar evolution code given in the orange line. The blue line shows the model that was mapped into phantom but not disrupted, but then mapped back into the stellar evolution code. And as you can see, there is a very good match between these two lines, which means that our mapping back into the stellar evolution code was good. And then we used that mapping to evolve all of our remnants. So we found that the remnants can live longer on the main sequence after encounter with supermassive black holes, hence elixir of life. As shown here, which this figure shows the luminosity on the y-axis as a function of time for middle-aged main sequence models of 1, 3, and 10 solar mass stars for a range of beta values. As you can see here, the more mass the star loses, the longer it can live on the main sequence. So how different are these remnants compared to stars which never encountered a supermassive black hole? So this figure here shows the evolution tracks of remnants in solid lines and the evolutionary tracks of stars which have the same mass as our remnants but never encountered a black hole in dashed lines. And as we can see for the terminal age main sequence and middle age main sequence models, the remnants formed are more luminous compared to stars which never encountered a black hole, which means that these disruption events result in overluminous stars. So in conclusion, stars can lose a lot of their mass and still survive. The cores rotate faster than the outer layers due to the formation of vortices. Stars encountering black holes can have found the elixir of life. They have more nitrogen in their outer layers, and they're also overluminous. Thank you.
So you mentioned that your models predict more nitrogen in the outer layer. So is it possible to make observation at any like spectroscopy that we could try to prove that will verify this is true?
So we looked at the nitrogen and carbon compositions as well for remnants at Kelvin-Helmholtz time. And for more strong disruptions, there is more nitrogen and carbon, which could possibly be used as a signature for detecting them.
Thank you very much for the presentation. This is a very interesting topic. But may I ask? Probably this is a very naive question, but I just want to be sure I'm not missing something. So you mentioned that in these simulations, the stars after the disruption event they can become overluminous, but they also live longer. I can imagine that this is because the only reason I can imagine this is because the core becomes, the convective core becomes larger, so that they can have a larger fuel available. Is that the case?
Yeah, they have larger radii. Yes. After
the core, the convective core itself, the mass. Because the idea that it becomes more luminous and also lives longer is, unless it has more fuel there, to me sounds like counterintuitive.
Yeah, it's more to do with how fast it burns the hydrogen and helium hydrogen in its core, because the CNO cycle is different, like for one solar mass compared to more larger stars. And that's why the compositions are different. And when the evolution does take place after the encounter, the rate of burning of the fuel is different, which results in more luminosity.
Mm-hmm.
Yeah.
Okay, thanks.
So you're using phantom to simulate this, right? So it's a basic question is, how do you include, so each particle is specified, like the chemical composition of the particle in phantom?
So
How-
in Phantom, there's like a mapping algorithm that was written by Mike Lau, and it tries to match the density profile of the stars in Phantom with
Yeah, but
the original
the
one.
particles are distinguished, right?
Yes. So it uses the
Chemically?
particles, yeah.
How do you do that in phantom?
Won't be able to describe the whole algorithm, but it uses entropy, and it tries to calculate the entropy, and I think that's how it redistributes it, but it's described in the paper, and I can send you the paper if you want to have a look.
Okay, thank you.